Peter Theodorus Landsberg was born in Berlin in 1922 and currently holds the chair at the Faculty of Mathematical Studies at Southampton. He is the author of a profound, prolific and diverse body of research ranging from electronics to biology via cosmology and the philosophy of science. Within this broad subject matter, he has always been particularly interested in one magnitude of physics, entropy, precisely a magnitude that has a great deal to do with the central question of this meeting. This interest is demonstrated by two things: his personal contribution to the subject, from both the thermodynamic and the statistical point of view, and his critiques of the contributions of other colleagues, some of whom are present here today. An interdisciplinary approach, research, discussion, and the teaching of knowledge are Professor Landsberg's stock in trade. And his ability to transmit stimuli is, once again, about to be demonstrated.
Well, ladies and gentlemen, I have written something, and I will more or less read it, because there are translators who I think have a copy, and it helps if I read it. But basically, I want to start by reminding you that there are many drives in the minds of men, and they've yielded results which are very astonishing. Powerful men have expressed their love for God, for fellow men, or their love for themselves by building big pyramids and temples and so on. And there are other drives which are, for example, for knowledge, for uncovering the laws of nature, for understanding things and for certainty. And they have given us courageous explorers who go, in spite of the climate, or even succumb to the climate like Scott did in the Antarctic, in order to map out distant lands. And this drive, human drive, has also given us great philosophical systems and scientific discoveries. And really, religion is also produced by a longing for certainty in our own personal life. The drive for certainty in the sciences, first slide please, is particularly inspiring. Do you think this, of course, when you talk about certainty, I don't know whether you can see this man. No. It is possible to see. It is René Descartes as being a representation of the human drive for certainty. Now there are two headings for our considerations of certainty. Certainty in mathematics and in man-made games like chess. If you have a checkmate position, that's certain and that's the end of it. And similarly, in mathematics, if a number is a prime number, that is also the end of it. But when we come to some big issues in mathematics, even there is a mist of uncertainty. And it is proved by, well, I can't prove it, but I will illustrate it by an example. I'm sorry. This is illegible at the back because the blackboard is not quite big enough. But it is basically this. I want to classify all adjectives into those that apply to themselves. W is W. Español is Spanish. English is English. And such adjectives are called autological. And if they do not apply to themselves, say the word long is really a short word, and if it does not apply to itself, it's called heterological. And so we have all these nice adjectives. We have two classes, autological and heterological, and maybe you think that is the end of it, but there is one further step. We have just invented two new adjectives, and so we should classify those. And now, suppose, therefore, we classify heterological. And here I show you that if you classify heterological, then you have a problem, because if heterological is heterological, if that is true, then it satisfies the formula W is W, and so it is autological. There is a problem. Or, if this is false, then heterological has to be autological, so it does not satisfy that formula, and so it is heterological. So there is a problem. And so what this comes to is that in a mathematical system, it may be incomplete. Incomplete means that there is a proposition A, roughly speaking, such that we cannot prove A and we cannot prove not A. That's incomplete. Or it may be inconsistent. There is one proposition A such that we can prove both A and not A. That's inconsistent. So, if there's nothing like that there, if there's no proposition like this, and there's no proposition for the inconsistent case, then you have a consistent and complete theory such that you can prove either the proposition or its negation for all the propositions in your system. But unfortunately, scientific theories are not of that type, and very often the basic result is, rather as in the case of heterological, that there is a proposition that cannot be proved or disproved, and such theories are incomplete. And in mathematics, insofar as it contains the arithmetic of ordinary numbers, these theories, as has been proved by Gödel, are incomplete. And so, there is some problem even in mathematics. Now, can I have the next slide? This is the mathematician. It is a mathematician. It is a picture of about 1490 or 1500. And if I can have the next picture, please, because I'm now going to talk about mechanics, and there is a picture by Francis Picabia, Parade Amoureuse, 1917. In man-made structures, we can exhibit uncertainty in crucial places, but let us consider the least likely candidate, the majestic structure of classical mechanics, long used for the precise calculation of solar eclipses for hundreds of years before their occurrence, and distinguished for the reliability of the tables for the tides. Our report on classical mechanics as a reliable discipline must be in glowing terms. It has even enabled us to place men on the moon and to bring them back again. And yet, there are some problems, even in classical mechanics. Consider a pendulum, like that. On its end, if you start it off a little bit on the left, it'll come down like that. And if you start it a bit on the right, it'll come down like that. But suppose one starts the pendulum from the top with the smallest experimental attainable error. Then the error can prevent a correct prediction. Sometimes because we don't know exactly where it is. Sometimes the prediction is right, and sometimes it is wrong. We are within experimental error. There's a 50-50 chance either way. Maybe the next slide was. It is still mechanics. Another machine. Classical mechanics has many situations where reliable predictions fail because there is a critical point where the smallest possible error can produce a large effect. And this is precisely where, even in classical mechanics, certainty has to be replaced by probability. So, can greater precision be attained by not modeling the system theoretically using a powerful computer? But we are again foiled. There is always computer error. A small initial error can grow larger and larger as the calculation proceeds, and eventually nothing can be said with accuracy if the calculation goes on for a long time. Probability and uncertainty enter simply because infinite precision is impossible, both in observation and in calculation. Eventually, with a little more complication, we come to systems whose perfectly deterministic equation yields randomness. This is the so-called chaos, and scientists have studied this topic along with catastrophe theory of our friend René Thoms, and it is attracting their interest. The key idea is that these systems are extraordinarily sensitive to the initial conditions under which they are started off. Now, of course, physics, what have we got? Machinery. Let us have a look at the next slide, just for the fun of it. Of course, physics has known probabilities for a long time. About 1860, both Maxwell and Clausius realized that there are so many particles in a system that one cannot follow the motion of all of them. If you cannot follow the motion of all the particles, you have to do the next best thing and introduce probabilities. Then we don't ask, what is the velocity of this particle? What is the velocity of this particle? But we ask instead, what is the chance of finding a particle with a velocity in a certain range? Certainty has to be jettisoned in favor of statistical information. This introduction of probability is of course important, but its philosophical significance is limited, because there was still a feeling that the introduction of probabilities was a convenience, but that it could be eliminated in principle by admitting incredibly complicated calculations or by engaging the services of a Laplacian calculator. So they developed the subject of statistical mechanics. Its probabilities are due to complications. And it makes us say, can I have the next slide? It makes us say that there will be rain with a 30% probability. Now, it is better without the light. It is called The Weather Witch by Wolfgang Hatter. The Weather Witch because the probability of rain is 30%. That is some prediction, but it is not enough. Because there will in fact be rain or there will be no rain. There will be no 30% about it. The meteorologist speaks of 30% chance because that is the strength of his belief. He cannot do better. We are still in a kind of statistical mechanics, even here. Mephistopheles is in the form of probabilities is here, but he's only just looking round the corner. And if you want to see him, I have a picture of him here, just outside. He's already attached and looking at you, round the corner. So that's classical mechanics, and now we will turn to quantum mechanics. When we discuss statistical mechanics, which arose at the turn of the century with Gibbs and Maxwell and Einstein, basically we were still in the year 1900. And then there came the then new quantum theory. This, you will remember, explains the wave properties of the smallest particles like electrons and protons, and it does so by the use of wave functions. It explains that energy comes in lumps called quanta, and it's a very successful theory. It can explain the behavior of particles on collision, the properties of metals. Electronics and semiconductors are also understood with the help of quantum theory. The theory is of interest because the wave functions, or the theory in its general form, applies, it gives you probabilities. The probabilities are the basic building blocks of the most basic theory. And that is important. After all, things actually happen in this world. and after they have happened, they are certain and complete. If we have the most basic theory, which yields only probabilities, one can ask, does there exist a better mechanics, which we will call an X mechanics, which assigns certainties? Is quantum mechanics merely the statistical mechanics based on the undiscovered X mechanics? It could be, after all, like the statistical mechanics, which is based on classical mechanics. And this idea works as follows. I'll give you an example. As being a teacher, a professor who has the unpleasant task of examining students and say they will pass or they will fail, suppose in an examination we are told that 70% of the candidates pass. The chance of any one candidate passing is 0.7 for any arbitrary chosen candidate. This is a probability statement. But if you study the past history and the abilities of each candidate separately, you might be able to say, this candidate will pass and that candidate will fail, and so on. This would correspond to the definite statements of the new X mechanics. In the end, of course, 70% pass, and this corresponds to the idea that quantum mechanics is the statistical mechanical version of this unknown and undiscovered X mechanics. Quantum mechanics works and is correct, but it does not go as far as X mechanics, this unknown X mechanics, would do. It is this search for X mechanics, the elimination of probabilities, as the basis of physics, that inspired Einstein's well-known remark that God does not believe in throwing dice. A famous paradox of the quantum theory is the following. It exhibits the problems of probability theory, and I have another slide here by Solomon Myers. Surprise contents. The next slide, please. It is a cat. It is a cat in a box. It is not easily to see, but it's a beautiful picture. A naive art. Imagine a box containing a radioactive substance which can emit radiation in a direction of a device which kills the cat. Radiation emitted in other directions is harmless. Assuming that the cat can be described by quantum mechanics, it is an alive or dead state with certain probabilities. When the observer opens the box, the cat is found to be alive, say. Could be dead, but suppose it's alive. We are optimistic. The probability has become a certainty. The question is, how does the probability of being alive get converted simply by opening the box into a certainty? Was it not certain before we looked that the cat was alive? Well, this matter has been discussed at great length, and one could say that quantum mechanics is simply the best theory we have, and if it makes probability statements, that's that. It is perhaps not the best theory yet. Some people say this example shows that quantum mechanics is incomplete, and some people will say that the application of quantum mechanics is here inadmissible because the cat and the box are large macroscopic objects, and quantum mechanics should only apply to the microscopic things. And some people may say, well, of course, we have a probability theory, and so it must not be used on a single individual system, but it can only be used on an ensemble of copies of the same system, and then one can show that for this interpretation of quantum mechanics, the Schrödinger cat presents no problem, because there are simply live and dead cats in our copies of the system. There are enough to represent the probabilities. The right number of live cats and the right number of dead cats representing these probabilities. It is really a bit like the 30% chance of rain, except in that case the probability is a subjective one. But of course there, if the meteorologist says 30% chance, if you want to know how good a prediction it is, you have to evaluate the meteorologist. You have to calibrate him. And then, of course, if you calibrate him over his past predictions, you will again introduce copies, more or less copies of the same system. You are again involved with an ensemble. Okay, this is not the end of our problem with quantum mechanics. It has an additional feature not related to the need for probabilities, and it is that it is not possible to think of quantum phenomena classically as existing in an objective state independent of the experimenter. The idea of the state of the particle can be given a meaning only if the procedure of observing it has been given. So the quantum mechanics withdraws the permission for us to talk about the state of a particle in some classical or objective sense. So, the search for certainty has come to an end here, and this is why I say that with quantum mechanics, Mephistopheles is not only looking round the corner, he's standing right in front of us, beguiling and convincing, but basically remote and enigmatic. Now, ladies and gentlemen, this seminar is called Determinism and Liberty. So far, the limitations of certainty in classical and quantum mechanics have been discussed here, and I have not even used the most obvious argument for indeterminism, which must surely be the principle due to Heisenberg that certain pairs of variables cannot be measured with accuracy at the same time. But actually we didn't need this principle. We were able, as you saw, to arrive at the impossibility of infinitely accurate measurements, even for classical mechanics, and even for one variable. When I talked about mechanics and this falling of the pendulum. But of course the uncertainty principle helps, because it gives us more additional and quantitative information. So if you look back at the book which Professor Wagensberg mentioned, Sidney Hook's book of 1958, and ask about the major changes in the intervening 30 years or so, we can perhaps say this: the foundations of quantum mechanics and the study of the paradoxes which may be formulated in that connection of quantum mechanics was in 1958 a highly specialized game, which professional physicists sometimes despised and often didn't take seriously. Now, the things are different. There are serious international conferences devoted to these problems. So, Einstein, who questioned with Podolsky and Rosen the foundations of quantum mechanics, was in this respect also ahead by about 50 years, ahead of his time. Now, determinism and liberty is our problem. Is there somewhere in modern physics a possible hint of determinism? We could look at the space-time continuum of relativity theory, in which the history of all objects can be mapped four-dimensionally. One coordinate represents the time, and the other three coordinates represent spatial distances. The creation of a particle and the decay of this particle are represented by points in this space. And the history of the particle, from its creation to its decay, are represented by a curve joining these 2 points. This curve mirrors the movement of the particle and its history, this history is therefore frozen into this diagram. The diagram is static. Each point represents where the particle is and when it is there. And the line is called the world line. Larger particles, we ourselves, are represented by world tubes because we have a certain size. Every object and every person has its own world tube. There, before our abstract gaze, lies our own world line, possibly fully determined with all future sorrows and joys. Perhaps it is in this sense that we can understand the quotation which George Wagensberg gave about what Einstein wrote about the death of his friend Michel Bessot. I'll repeat it. Michel has left this strange world just before me. This is of no importance. For us convinced physicists, the distinction between past, present, and future is an illusion. So the existence of one world tube in a static four-dimensional framework does not, however, imply determinism. It merely shows that definite things happen. Whether these things are fixed by prior causes or by chance, that is quite another question. So, now I want to discuss in this framework of relativity theory for a little while the question of indeterminism. At first sight, the possibility of free will is increased by indeterminism, because indeterminism allows for chance events happening by accident. But these, if they influence the agent's brain, his actions, though apparently due to free will, also may reflect an element of chance in his brain, even if he doesn't realize it. Is he really free, or is he subjected to chance events in his brain? So that is arguing from indeterminism. Chance events in the brain. Now we argue from determinism to get to the same conclusion, right? So you have to remember what I said about indeterminism, chance events in the brain. Now, if you have a deterministic universe in which individual actions can certainly cause definite results, but it is then a question if these actions are themselves predetermined, because we are now assuming determinism. So although we can do what we want to do, are our wishes to do certain things themselves predetermined because there is determinism? Is the agent as free as he thinks? Here one can see again the possibility of this intermediate position. While the human agent thinks he's free, outside students of his brain may conclude that he is laboring under a misconception that his actions are in fact predetermined. Now, the proper analysis of this is rather subtle, and I'm sure that it will give us a chance in the discussion to clear it up. It depends, for example, on how you define free will, and there are various ways of doing this. So while relativity is a deterministic theory, this deterministic feature becomes less certain once we introduce the observer. And this I want to see next. I'm afraid it is a slide which you cannot see. A slide, next slide please. This slide you probably all know, if you can even see it. It is Salvador Dali's Temptation of St. Anthony. It's a beautiful picture, and I used it for illustrating quantum mechanics. Where has reality gone? And the next slide. Well, this slide is to show those of you who are not too familiar with relativity or space-time diagrams that if you have an observer down here at this point O, time goes up this way, and light and the x coordinate is this way, and you can be reached, you're sitting here at this place in time and space, and a signal from here can go up here. That's a slow signal. It's slow because it covers only this distance in that time, in this time, only that distance. There's another, you can also be reached by this event from B. It's a bit faster because in this time it now covers a bigger distance. And if it's as fast as possible, it will be a speed of light, and it'll go from this point, which I've labeled C, although you can't see it, goes from this point to there, and that's the fastest. This distance is covered in that time. So, you have a light cone, all this information can be fed into you, but this cannot. And similarly, that's your past light cone, and that is your future light cone, where you can influence the future events, provided your signals don't go too fast. The fastest they can go is this way, velocity of light, and they can go more slowly. So there are the events you can influence. So there is a region in between, which is shaded vertically, that refers to events which cannot interact with you at O. And it's easily seen, therefore, that there is some possibility, you might think, of determinism, because, but there is an uncertainty because of those events. Are they in the future or are they in the past relative to you? It is indeterminate. Now the next slide, in this next slide I will explain that on the basis of these diagrams you could even think of relativity. Frozen world lines, your own world line determined from birth to death, everything fixed. Apparently everything is determined. Yet, here is an argument of a sense in which even relativity allows for indeterminism. As you travel from O up in time to O dash, because of this business of the light cone, you can receive events from here, signals, and things can interact from here with you here. But as you progress to here, new events can enter and influence your life or your activities, namely all these events that come from this light cone, which includes more than that light cone. So in that sense, in some way, things are not completely determined. Okay, now, ladies and gentlemen, I come to entropy. By the way, Mr. Chairman, I have time. How long more? I don't want to talk for too long. Half an hour? Have I had half an hour? How long have I had? Another 20 minutes? That's fine. So entropy, there is a theory, ladies and gentlemen, which is rather fantastic. But I will mention it to you, according to which different universes are created each time there is a transition. Now, it is a serious proposition that all these universes are created, but they can't get into contact with each other. And that is called the many-world interpretation. And according to this, there exists a universe other than this one, in which, for example, there was no recent earthquake in Mexico, and there may exist another universe among the millions of possible universes in which there is no life. But I want to cut this possibility out, and because it gives you rather a lot of what we might call scientific excess baggage, because you can't test these possibilities. So I will assume that there is only one universe. This is it. What then does it mean to have a probabilistic universe, as I have it in my title? It's a universe in which human limitations and ignorance limit predictions and probabilities. But these, later on, turn into definite events. The uncertainties of the future become the certainties of the past. Into such a universe of future probabilities, scientists have had to introduce statistical quantities, probabilities, and one of them, probabilities, distribution laws, but also entropy. Each probability distribution has an entropy. I want to explain the meaning of this term. The next slide is a slide by Mondrian, a very simple one, just a red square, and some white and yellow squares. It is tidy, a tidy thing. If we tidy away all our children's toys in a toy cupboard, the probability of finding a toy in a cubic centimeter is highly packed in the region of the toy cupboard. This corresponds to low statistical entropy. Release the randomizing influence in the form of an untidy child, and the toys will be all over the place. A widely spread probability distribution results for the toys, and we say that the statistical entropy has increased. The uniform distribution of toys over the room gives you a maximum probability. Slightly higher probabilities, higher entropy is the next slide, which is the Bruegel's Schlaraffenland. People are drunk. So that's slightly higher entropy. And even higher entropy is the next one, the next slide. I'm sorry you can't see it. It's by Kurt Schwitters. It's a montage. Everything seems to be random in it, and that is really the highest entropy of all. Now, the business about the toy cupboard seems somewhat trivial and simple, but one can use it. We can define disorder as the actual entropy divided by the maximum entropy. In a physical system where you can measure entropy, we take it as the ratio. That shall be disorder, right? The actual entropy divided by the maximum entropy. So if that is 1, because the numerator, the entropy in the numerator is the maximum entropy, then that is maximum disorder. So entropy divided by maximum entropy is a measure of disorder. It seems a simple thing to do and means nothing. Yet it can be used because we've decoupled entropy and disorder. Now, under normal conditions, entropy and disorder increase together. But it need not always be so. Suppose the room is tidy. The toys are in the cupboard. Now the cupboard is allowed to expand. Then the actual entropy increases because the toys may now be anywhere within a bigger volume because the toy cupboard has become bigger. But suppose in addition that the room expands even more rapidly, then the maximum attainable entropy has also increased because the toys can be spread over a bigger area. And so the ratio of entropy over maximum entropy has actually got smaller because although the top increases a bit, the bottom of the fraction increases even more. And so in this sense, the maximum attainable entropy, we have a remarkable result that entropy goes up and disorder goes down. And it is in this case, in this sense, that entropy and order could sometimes increase together. And the reason for noting this possibility here is that biological systems grow, the universe expands, and there are many other systems that change their size. And so the toy cupboard, simple analogy, is quite useful. Now, it is because the universe is probabilistic, we can talk even about the entropy of model universes. The entropy increases normally, and we can understand by virtue of the ideas just introduced that the universe, as it expands, could also get more ordered. So next slide the heat death of the universe, or the end of the universe, well, here we have Giotto, the Bondone, the Last Judgment picture in Padua. That is the end of the universe, according to some of us. You could see the damned souls on the left, Sinestre, and on the right, those that go to heaven. Anyhow, is that the end of the universe? Not if you believe in an oscillating universe. Or because after the oscillation, at the end, this is not the end. There will be, on the next slide, a new beginning. This is a slightly unconventional interpretation of Michelangelo's creation of a man. Oh, that should be the other way around. First, can I have the next one first? The creation of the world by Michelangelo, but interpreted as the beginning of the next oscillation. It's in the future, because we have the possibility of an oscillating universe in which perhaps when life has died down, it may come back again in some form in the future. And so the creation of man, which is the other slide which you've seen, would come next. So, the scientific enterprise cannot, in my view, furnish definite answers to the puzzle of determinism. Will it ever be able to do so? I believe that human brains put together are too weak a tool to even elucidate the workings of another human brain. But of course, great advances will no doubt be made, but the basic question of determinism will, I think, not be answered by science. Some people are more optimistic. They believe that science is on the verge of answering such questions as what is matter, what is life, what is mind. To me, it seems impossible to do that. Scientific method does not lend itself to such tasks, which would lead to ultimate truths. I think these are not for men, these ultimate truths. They are perhaps for God. The marching orders of the scientists are from effect to cause, and from cause to effect. This method is unsuitable for the study of first causes. A first cause is a category of thought which does not exist in science. The causal chains are long for scientists, and they disappear from the view of the diligent scientists in the mist of uncertainty and in a sunset of doubt. On ultimate questions like the origin of the universe, or the make-up of the ultimate constituents of matter, or the existence of God, science has to be silent. Only faith can be a guide in these cases, and this means that one is in the end dependent on the convictions and emotional preferences of the individual. Thank you.